Hello and welcome to section 2.6, Special Functions. Today we are going to be building off the previous day stuff when we are using equations in slope-intercept form. Also, this video will be split into two separate pieces just because I won't have enough time to get everything in I need to get in 15 minutes. So, regardless, here we go. Starting with our first vocab word. Our first vocab word is a piecewise defined function, which is exactly what it sounds like. It is a function that is written in two or more expressions. And so we start off with one right away where we have graph of the f of x, and here are the two functions. Now it is stating the part of the domain that it is in, the part of the x values that it is in. So now when we do these problems, how do we do these problems? Well, the first thing you want to do is to bring it down. So I'm going to bring this whole thing down here. So it's going to be x minus 2 if x is less than negative 1. The very first thing after you bring it down, what we have to do is to put negative 1 in for this x. So negative 1 minus 2 is negative 3. So now we found the point. Our point is now negative 1, negative 3. So when we first plot this point, we go over to the left 1 and down negative 3, and it is going to be a open circle. And why is it an open circle? Because our inequality is just a less than sign. And if it was equal to, then it would be filled in, but it is just less than. Now, looking at our slope is whatever is attached to our x, whatever is in front of our x, and here we find our slope is just 1. So now from our open circle, let's put in our slope. Well, since it is 1, I would go up 1 and over 1, but we have to look at our domain. Our domain says that x is less than negative 1. Well, here is negative 1. We can't go past negative 1 going right because that's on the greater side. It wants to be less than. So we can only go this way. We can only shade on this side or put points on this side. So now, if our slope of 1, where would we put our slope? We would go to the left 1 and down 1, left 1 and down 1. Now we have a couple points that can be connected by a line. So we can go ahead and connect those points with a line. So I have an open circle with a line going through and an arrow on the end. Now we're not finished because we need to do the second half of the piecewise function. So I'm going to put this part in blue. So again, to start off with, you go x plus 3, and if x now is greater than or equal to negative 1, once you rewrite it, the first thing we have to do is put negative 1 in for x. We add 3 to get a positive 2. So now our coordinate point is negative 1, 2. Now we put a point on negative 1, 2. And what kind of point are we going to put? We are going to put in a filled in circle because of the equal to sign. Right? We left the red one open because it was less than. Now this one we have to fill it in because it's equal to, because of the equal to underneath there. Now again, what is our slope for this line? Our slope is going to be whatever is attached to x, and there is a 1 attached to x. So now we go up 1 over 1 depending on our range, and we're looking at our domain, and our domain says that x is greater than or equal to negative 1. So again, here is that negative 1. It is greater than that negative 1, so we can only draw points on this side of the graph. So from our point, we can go up 1 over 1, put a point, up 1 over 1 for the slope. Now we have a couple points that we can connect. So then go ahead and connect those points. So there is the graph of the piecewise defined function. Now we're asked to identify the domain and range. The domain is our x values, correct? So the domain equals the x's, which equals, now, if I'm looking at my x values, are all of these x values used up where my cursor is? Yes, those x values are used from this line. How about going this way now, where my cursor is? Are all my x values used on this side? Yes, because my line is keep going up, 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 all the way until it's off the screen. So my domain values are going to be real numbers, while my range are my y values. And so now we start down here, and we get to -3. Well, notice how we don't have a line from here to here. So now y is less than -3, and y has to be what? Y has to be greater than or equal to, because it's a filled-in circle, equal to, and what is this point here? 2, because we're at y2. So now we have the domain is all real numbers. The range is y is less than -3, and y is greater than or equal to 2. Now, let's work backwards. Now we're going to be given the graph of a piecewise defined function, and we're asked to write the expressions. Well, what I like to do is I like to break it down into separate lines. So I'm going to start with this blue line. You could start with the blue, purple, or red, but I'm going to start with the blue line. What we have to do is to put it into slope-intercept form. So y equals mx plus b, where m is your slope and b is your y-intercept. So on the blue line, let's first find our y-intercept. So our y-intercept is right there. B is going to be 3. Now, what is my slope going to be? Well, I have an intercept here, and I have an intercept. It goes through a coordinate right there. So now I have 2 points. Well, what is my slope going to be? It's going to be down 1, 2 over 1, and it's going up from left to right. So my slope is going to be 2. Now, if you can't find a coordinate plane or parts of the grid that the line goes through, then you can just pick your 2 favorite points on the line and then use your slope, which is y minus y over x minus x, to find your slope, and then you can go on from there. But since it's already given to us, I'm going to use it just from the line. And so now when I put this into my expression, I have y equals, my slope is 2x plus 3. And now, when is that though? We have to state our domain if, and then we have x is what? Well, we have every number up until what? X is 1, and that's on the less than side of x is 1. So if x is less than 1, so here is one part of our piecewise function. Now, looking at the purple line, starting with our y-intercept, if we would continue this line over here, where would it cross? It would cross at 3. What is the slope of the purple line? I'm not going up any, but I'm going over. So my slope is 0 over 1, or just 0. So now let's put that into the line, or that into the expression. Y equals, our slope is 0m plus 3, also known as y equals 3. And then we have to state the domain if, and then how about our x's? If x is what? Here's where it starts. So if x is, and it's on the greater than side of 2, so if x is greater than 2. Now looking at the red line, y-intercept, if we would continue this line, it would go through where? It would have a y-intercept of 2. It has a slope of, goes down 1 over 1, has a slope of -1 because it's going down from right to left. Plugging it in, we have y equals a negative x plus 2. And what is our domain? If x is what? Bigger than, here's 1. If x is greater than or equal to 1, and x is less than or equal to 2. Now if you wanted to, you don't have to, but you could go f of x or y, so you could label this y, or you could go f of x, function notation, and then the brackets, what you saw on that first page, 2x plus 3. If x is less than 1, then your purple equation, y equals 3 if x is greater than 2. And then finally, we have negative x plus 2 if x is greater than or equal to 1 and x is less than or equal to 2. Now, we're going to get into some more vocab. A piecewise linear function is a function in which the equation for each interval is linear. And some examples of a piecewise linear function would be a step function, which is a piecewise constant function. Now, probably the most known of all the step function is the greatest integer function. And what we have is this guy right here, which is the greatest integer function. The step function notation is these brackets in red, usually denoted by brackets. So they'll either be brackets, or in our book they're double bracketed. What that means, the greatest integer function, what that means is to find the greatest integer less than or equal to x. So if it was 1.5, you would round down to 1. So if you want to think of it in different contexts, you're just rounding down. So the greatest integer function, all that means to you is to round down. It is the greatest integer less than or equal to x. So let's take a look at some of the examples. So if we have f of x equals the greatest integer function, we're putting that 2 in for this x. So it would be 2 would be in our greatest integer function. So f of 2, that really changes nothing. It would just be 2. Same thing with a negative 2. It'd still be negative 2 because it's right at that whole integer. Now, though, if we went to 1.45 or 1 45 hundredths, right in there, correct? Well, we would have to go back to the greatest integer less than or equal to, or we would just round down to 1. But we have to be careful with negative 1.5, because there's negative 1.5, right? We're coming from the left. What's the greatest integer less than? Or if we round down, it would be negative 2. Well, how about pi? Pi is 3.14. It's right there. We pass 3. We round down to 3. How about negative pi? It would be right there. It's really close to negative 3, yes, but we have to round down all the way to negative 4. And I'm going to stop the first video right here before we get into graphing the greatest integer function, and we'll pick it up on the next video of graphing the greatest integer function and absolute values. Welcome back, ladies and gentlemen, to the second part of section 2.6, special functions. With number 1, notice how we have step notation donated by those brackets. Now, when we have that, usually in most tables, we would pick 0, 1, 2, 3, 4. Well, when we have step function notation, we have to have a range from 0 to 1, right? And then we go from 1 to 2, and then we can go 2 to 3, and 3 to 4. And you could go down this list, doing the same thing. Well, now when I say 0 to 1, that means I can pick any number 0 to 1. I'm going to round down back to 0, right? So let's put 0.57 in the brackets, correct? Well, 0.57, we would round down all the way to 0. And now 1 to 2. If you pick 1.5, we would round down to 1. Or 2.2, we would round down to 2. And then let's put 3.9. It's not quite 4. We're looking for the greatest integer less than or equal to that, and it would be 3. So now what does this look like on a graph? Well, 0 to 1 is right here on my x, but it's at the y of 0. So here, now it's going to be a closed point to a open point. And now I'm going to do 1 to 2. I go 1 to 2, and that's at y is 1 or f of x is 1, where my f of x value is 1 or my y would be 1. 2 to 3. So I find here's 2 to 3. How high do I go? I go up 2. So I put a point, and I have a open circle with a bar, or open circle with a bar attaching it. And then 3 to 4. Here's 3 to 4. And where is it on the y? It is at 3. So I move it up. Again, it's a closed circle because it can be that. And then bar, open circle because it's not that. And now this would continue in both directions. And here is where we get our steps because it looks like a staircase. Now with number 2, when you have a 2 attached to your x inside that step function, we want to get it to look like this essentially. So with whatever's attached to it, we want to get it to be 1x. Well, what would I have to multiply this guy to get it to be just a simple x? I would have to take it times 1/2. So whatever you have to take it times, that's what is going to be our intervals for our x. And so here it would be 0 to 1/2, 1/2 to 1, 1 to 1 and 1/2, and then 1 and 1/2 to 2. So let's try it out. What would happen if you picked 1/4? That's between this guy. You pick 1/4, it becomes 1/2. Well, anything in this value you round down to 0, so it would be 0. 1/2 here, you plug it in. You plug it in for this x. 1/2 times 2, you'd have to round down because it's 1. This is going to be 1. Then you plug 1 in. It turns out to be 2. You plug anything in this interval, you would find out that it rounds down to be 3. And so let's take a look at graphing this guy. Now it's 0 to 1/2, and it's y at 0. So 0 to 1/2 looks something like that. 1/2 to 1, and we're at y of 1. So let's put a point, open circle. And then 1 to 1/2 at 2, so we put a point, and then open circle. And then 1/2 to 2, we have 1/2 to 2 on my x, point, open circle. Again, notice that we have the steps going in both directions. They are just shorter steps now. Now looking at 3, now we have a 1/2 x. Remember, we want it to look like that. So what do we have to multiply it by? We would have to multiply it by 2. So now our steps are going to go in intervals of 2. So we have 0 to 2, 2 to 4, 4 to 6, and 6 to 8. You can plug anything from 0 to 2 in this x, and you would have to round down to 0. You would plug anything from 2 to 4 in for x, and you would have to round down to 1. Then you go from 4 to 6. Anything in that value would be 2, and anything in this value would be 3. Now let's try to graph something like this. Here we go from 0 to 2. So I put my point at 0 to 2 and go all the way to 2, and that's at y of 0. And now I go from 2 to 4, which is this range right here, and I go up for y is 1, point, open circle. Then 4 to 6 is right here. I go up 2 for that interval, and then 6 to 8 is right here, and I go up to 3. Notice that this would continue in both directions. Let's try one more example with function notation. Now notice how this 2 is outside the step function. So when it's outside the step function, we can just pick our normal intervals. So we're going to go from 0 to 1, 1 to 2, 2 to 3, and 3 to 4. Now we have to be careful when we plug things in. So 0 to 1, I'm going to pick, you can pick any point, but I'm going to pick, let's go with 0.5. Now that 0.5 is in the step function notation, or is in the greatest integer function, and now we would round that down to 0, correct? So then it would be 2 times 0, which is 0. Then we would have 2 times 1.5. Again, you can pick any number inside 1 to 2. Now this 1.5 would round down to 1, so 2 times 1 would be 2. And then same situation here, it would be 4, and then 6. Again, now we have to plot these. 0 to 1, right here is at 0. Then we have 1 to 2, which is here, but it's all the way at 2 now. Then we have 2 to 3, which is right here, but it's all the way at 4. And then 3 to 4, and it's all the way at 6. Now let's move on to a word problem. Here we have a psychologist charges a counseling session at a rate of $85 per hour and any fraction thereof. Now we're asked to draw a graph that represents this situation. Well, $85 per hour tells me no matter how long I go, I'm going to get charged $85. So as soon as I step in the door, I'm going to get charged $85 all the way up until that first hour. Now from hour 1 to 2, I'm going to get charged double that, right? So I'm going to get charged $170. And then from 2 to 3, I'm going to get charged 3 times the amount. And it's just going to be keep going up and up and up. Now we're going to move on to an absolute value function. When we have an absolute value, how do we represent an absolute value? Remember, it's with those bars, right? It's straight up bars. Now, when we fill in tables for this, we want to put in 0. We want to have 0 in the middle of our absolute value. So I have half of it done for you, where 0 is still 0, 1 is 1, 2 is 2. Now, though, if we put negative 1 in for x, the absolute value of negative 1 is 1. The absolute value of of negative 2 is 2. Absolute value of negative 3 is 3. So if we plot these points, negative 1, up 1, negative 2, up 2, negative 3, up 3. And now what kind of graph are we going to make? We are going to make a graph that looks like a V. So we need, for an absolute value function, we need to have a graph that looks like a V. Again, we need a V. For the absolute value function, we need a V. A V. Now, when we move on to this blue guy, notice how this x is all alone, all by itself in the absolute value. With that being all by itself in the absolute value, it is fine. So then the middle value we would have in our table would be 0. We would plug that 0 in for x. Now, once you have your middle value in your table, you can put negative numbers in and then positive numbers in from that point. So it would be 1, 2, and 3. And then going down, it would be negative 1, negative 2, and negative 3. So now if I put 0 in for that x, it would be 1. If I put 1 in, it would be 2, 3, and 4. Now if I put negative 1 in, be careful here, ladies and gentlemen, negative 1 is actually a positive 1, so it would be 2, 3, and 4 here as well. So if we would graph this, we would have 0, 1. We would have 1, 2, 2, 3, 3, 4. We would also have negative 1, 2. We would have negative 2, 3, and we'd have negative 3, 4. We could then connect our dots with a line. And so again, we have a graph that looks like a V. Now be careful though with this red guy, because notice how we have x plus 1 in there. We want this whole guy to be what? We want it to be 0. What do we have to put in for x to make this 0? It would be negative 1. So now we're going to start at negative 1 and move up and then move down. So we move up to 0, 1, and 2, and then we move down negative 2, -3, -4. So now, if I put -1 in for my x, it would be 0. If I put 0 in, it would be 1, and then 2, 3. Now if I put -2 in for that x, it would be a -1, but the absolute value of -1 is +1, and then it would end up being a +2 and a +3. So now let's graph this. So 0, or it goes -1, 0. So I go -1, down 0, put a point. Then I go 0, 1, 1, 2, 2, 3. Now moving to the other side, it's -2, up 1, -3, up 2, -4, up 3. Now we connect those dots with a line, and notice what the 1 inside the absolute value does to my graph compared to outside. The 1 moves it over, and the 1 outside moves it up. And then finally, I just want to reiterate, step functions, we want to get that x to 1. Remember, we want to get that step function to look like just x. And then absolute values, we want to have 0 in the middle of the table. So here, and I'm sorry, this should be an absolute value. So here, the middle value in our table would be 0, but x plus 2 in an absolute value, our middle value in the table would be -2. And that's it for section 2.6, special functions. Good day.